So chapter 3 is going to tell us all about something called an electric field. And an electric field relates to some concepts that we've already studied in physics. In particular, it refers to something called action at a distance. And where we've seen this before is in terms of forces. And in terms of forces, we have things like gravity, things like the electric force, that make things happen. And they make things happen across huge distances. So gravity acts at a distance. Think about the example, for gravity in particular, of the sun acting on the Earth. The sun keeps us in orbit. The sun isn't right next to us, it's not touching us, it acts at a distance. So action at a distance. This is the interaction of a force despite being separated by a huge distance. And we know that forces act at a distance because of a field. So forces act / are carried by what we call a field. And in the case of electricity, electrical charges create these fields. Any charge creates an electric field. Electric charge creates electric field. And when charges interact inside of this electric field, that's when you get an electric force. Electric charges creating an electric field. And these charges interact with the field through the electric force. So let's see a little sample of how this actually works. So what I can do, I can draw a charge, some charge Q prime. This charge creates some kind of electric field. I'm just going to draw electric field here. We'll figure out how this actually works a little bit later on in the chapter, but I'm going to draw all these little lines. And these little lines represent my electric field. So every line you see is a little piece of electric field that's coming off of this charge. And as I mentioned, the electrical charges interacting with this field is what gives me an electric force. So I need to bring another charge in here, some charge Q. This charge Q is going to see this field right here. It's going to see the field that it's inside of. And that field depends on how far away it is from the charge that's making the field, in this case, Q prime. What I can do, what I've already done, what we've already talked about, is the force that these two charges feel between each other. The force they feel is the Coulomb force, and that's equal to K times Q prime, the charge making the field, times Q, the charge that's inside of the field, divided by R squared. Now, if I want to know the field that I'm interacting with, my charge that I'm bringing in is Q. So to figure out what the field I'm in, the field is the force created by this charge Q prime divided by whatever charge is inside of that field. So in this case, my electric field, E, is equal to F divided by Q. And I can plug in my Coulomb force, the Coulomb force that we figured out up here, the force between my two charges, and that electric field is K times Q prime times Q divided by R squared. And then I still need to divide by my Q, because my electric field E is equal to force divided by charge. So I divide by my Q. I see my little Q's cancel, and my electric field of some charge is equal to K times whatever that charge is, Q prime. Remember, we're figuring out the charge, the field created by this charge Q prime. That's what all these lines are, the electric field created by that charge, divided by R squared, the distance you are from that charge. So the electric field depends only on K, the charge that's making the field, and the distance you are from that charge. This is a very useful definition for electric field, and we can also remember the alternative equation in terms of the electric force. E is equal to F divided by Q. These are two useful equations for you to know. So like much of physics, we're interested in what we're actually physically representing here. So the electric field equation we have is electric field is equal to force divided by charge. So if I want to know what the electric field represents, I need to figure out the units. So the units of the electric field are going to be equal to the units of the force divided by the units of charge. The units of force are newtons, the units of charge are coulombs. So the electric field is newtons per coulomb. And as you're studying your book, I suggest reading the problem-solving techniques on page 728 to figure out how to add multiple electric fields. So if you have a bunch of charges, how do you sum up those electric fields? It's going to be a very similar process to how we usually add multiple forces together. We have to do vector addition to figure out total magnitudes of electric fields for multiple charges. That's going to be the algebraic approach. And you should be able to understand and figure this out yourself by reading the book and going through some of the examples. If you don't, then send questions. I'm going to talk about is what we do if we have lots of charge. And by lots of charge, I mean more charges than we can individually write down. In this case, we treat charge distributions, we treat charges as being smooth rather than discrete. Smooth rather than discrete. So in this case, I don't have individual charges that I'm going to add up. I have functions, I have equations that represent charges, and I'm going to add those up by using calculus methods, something called integrals and integration. So in this case, we're going to start utilizing calculus. We need to rewrite our definition of the electric field. The electric field is now some differential element, some piece of an electric field, dE. And that's going to be equal to K, which is still a constant, times dQ, little differential small pieces of charge, divided by R squared, the distance I am from that little charge. So this is very similar to our regular equation, except these D's mean that we're working in terms of differentials, in terms of derivatives. So instead of treating a charge distribution as one separate little charge, we're going to take that charge distribution, we're going to break it up into little pieces. Each one of these little pieces is a little piece dq. And we need to add up all these little dq's that we have inside of this distribution to get the total charge. And we're going to do that using calculus. And the real key in solving this problems is going to be finding and understanding what dq is. This dq tells you all about the charge, and it also depends on where the charge is distributed. In this sense, it's kind of similar to the moment of inertia that we talked about in Physics 1, where we had mass and where the mass was. dq tells us charge and where the charge is. If the charge is along a line, then we're going to have this differential charge dq is equal to something called lambda times dl, where lambda is equal to the amount of charge you have on something divided by the length, and dl is a little piece of length. So what does that look like? What am I talking about? This is saying, let's assume I have a stick, some kind of rod that's creating charge. Maybe this is a wire. And I have charges flowing around through this wire. And what I'm going to do, I take this little wire and I break it up into pieces. Each piece has some little length. Each one of these little pieces has a little length. Okay, each one of those little pieces is a length dl. Each one has some charge associated with it, some charge in that amount of length that's equal to lambda, and I can combine these two to figure out what dq is, the amount of charge that's in just this little shaded piece, just this little red piece. And then I take that and I add up a whole bunch of little dq's. I'm breaking this up into a whole bunch of tiny little pieces. Each one of those pieces is a little dq. And I add up all the dq's, and I'm going to add up all the dq's through the purpose of an integral from 0 to the whole length of this little piece of wire. So that's kind of the idea of what I'm doing. I'm breaking my wire up into little charge pieces. Each charge piece has some charge dq, and that dq depends on the charge per unit length inside of this wire, and it depends on the length of each of these little pieces. So how wide these little pieces are would be that length dl. Okay? So we don't always have charges just distributed along a line. Sometimes we have charges distributed along a surface. In the case of charge along a surface, things look a little bit different. For charge on a surface, we have our charge dq still, but that's going to be equal to sigma times dA. In terms of a surface, we're talking about a two-dimensional body. So our sigma is going to be the charge, but it's not spread over a length like our charge along a line. It's going to be the charge divided by the area. The charge divided by where it's spread out. And dA is going to be a little differential piece of area. And finally, charge on a volume. It's the same idea as the previous two. We still have some little piece of charge dq, but that little piece of charge dq is now equal to the Greek letter rho times dv. And if you can guess, if you're seeing the pattern here, rho is going to be equal to the amount of charge. We're still talking about charge and how it's spread out, except this time we're talking in 3D, so we're talking about spreading charge throughout a volume, some three-dimensional body. And dV is going to be your volume, your little differential piece of a volume. Now let's try an example working with this so that we can see how this is going to work. Okay, so the example we're going to work on an example where we have charge spread along an infinitely long, straight, thin rod. And the charge per unit length on that rod is equal to lambda. What is the electric field any distance that I go from this rod? So I need to figure out the electric field. First, let's draw a picture. What does this situation actually look like? Let's say I have an infinitely long, straight, thin rod. So here we go. Let's assume this is infinitely long, so it keeps going up and it keeps spreading down to positive and negative infinity. If I'm going to do this, then I probably want some axis that I can do everything relative to, so I'm going to draw an XY axis. So I can figure out what's going on in the X direction and figure out what's going on in the Y direction. Now the way I've set this up in the Y direction, that's the direction of my rod. And in the X direction is the distance that I can go away from my rod. So let's say I go some certain distance out here. I want to figure out what is the electric field at this distance away from my rod. Let's draw what those electric fields kind of are going to look like. Well, I'm going to have a little piece of charge, some little piece that I'm going to break my rod up into. So we'll call this my first little charge piece, DQ1. And I'm going to have a DQ2 and a DQ3, 4, and so on and so forth, all the way down to where I get to a DQ2. We'll call this one DQ2. And we'll say that this top one is some distance d away from the middle, and the bottom one is some distance d. So these two, DQ1 and DQ2, are equidistant from this origin point. So I have this charge element here from DQ2, and it's going to create an electric field. It's going to create a field that this charge that I'm talking about, the charge that I want to find the electric field at, it's some distance away. And it's going to create a field. If we draw our field lines, maybe the field's going to go like this. We've drawn some fields already. We'll figure out how to draw electric fields in just a minute, but for now our field points away from this charge. We're also going to have a field from this top charge that's pointing away and acting on our charge and pointing kind of the opposite direction, kind of the opposite way. And what we're going to see is that the electric field from this bottom part of the line is going to cancel with the electric field from this top part. But it only cancels in one specific direction. If you recall, when we're adding electric fields, we need to be concerned about direction. We need to separate it into the X and Y direction. So we have some little piece in the X direction and some little piece in the Y direction. Some little piece in the X direction and some little piece in the Y direction. What we see here is E2Y is equal and opposite to E1Y. So all the Y direction electric fields are going to cancel each other out. But if we look closely, we can see that E2x, which is acting to the right, is equal to E1x, which is also acting in the x direction. So they're going the same direction. So the x direction fields add together. They don't cancel. So we're going to need to figure out what those fields are. All right, so how do I figure out what the fields are in only the x direction? I want to separate out, I want to yank out only the x components. E2x, I only want E2x, I only want E1x, and so on and so forth. Remember, we break this up into multiple little infinitesimally small pieces. So I don't have just this top second piece each, this top piece 1 and this bottom piece 2. I have all these pieces in between. So I have an infinite number of little pieces along here, and I want only the x components of those. So I have to turn to some trigonometry to figure this out. First, we write our equation for our electric field. Our electric field, in terms of differentials, is dE is equal to k times dq over r squared. But I don't want the whole electric field. I don't want all of E2 and all of E1 because the y directions cancel. I want only the x pieces. So if I look at the angle that these fields make with the x-axis, the angle is theta, and if I want only the x component, the adjacent side of this triangle that I've drawn, then I'm going to want dE in the x direction has to be equal to k times dq over r squared times the cosine of the angle. I'm selecting out only the adjacent component because that's the only component that is contributing. Recall E2y was going up, E1y was going down, and they cancel each other out. So we want only the x pieces, only the x components. And that's what this does. This cosine of the angle selects out only our x components. This is a charge distribution with charge distributed along a line. So if we have charge distributed along a line, we should remember that dq for a line is equal to lambda times dl. Okay, so let's take a look at this. Let's plug in our dq. We'll find that dE in the x direction is equal to k times dq over r squared times cosine theta. Again, this is just a review. We already know what this is, and we know that dq is equal to lambda times dl. So I can plug this in for my dq, and I'm going to do that. I'm going to plug in for my dq. dE in the x direction is k times lambda times dl divided by r squared times cosine of theta. Going between these two steps, all I did was plug in for dq. Look closely and you'll see that that's the only thing that happened. Okay, now we need to look a little more closely at what this dl is actually referring to. I can draw my picture again. We have our x and our y axis. And we have our charge separated, distributed along a line. Maybe this is charge in a wire. So this length, dl, this little bit dl of this little tiny piece of charge, this tiny differential piece of charge up here, is some distance dl along my wire. So my dl is along a specific axis. The charge is distributed along this dl, so my dl in this case is along the y-axis, so that's just going to be dy, because that's where my charge is. My charge is distributed up and down along the y-axis. So my dl has to be dy. So now I can rewrite my equation for my dE in the x direction has to be equal to k times lambda, and instead of using dl, I'm now going to plug in dy because the charge is distributed along the y-axis. And it's still divide by my r squared, and I'm going to multiply all of that times cosine of theta to select out only that x component. So when we get to this is most of the physics right here. Going on from here requires a good bit of math trickery. So I look at my equation for dEx, and that's equal to all this mess over here on the right-hand side. The equations, the variables that I don't know. I don't know what dy is, I don't know what r is, and I don't know what theta is. Okay, so I have three choices of variables that I can try to integrate over. Right now I have it so that the variable of integration depends on what I'm differentiating with respect to. So I would be integrating this over dy. If I integrate over dy, that's going to get kind of tricky, because dy, since this is an infinitely long wire, is going to go from negative infinity to infinity. I don't like integrating from negative infinity to infinity. So I'm going to look and see what happens. What if I had somehow, some way, I got some, instead of r's in here, I got some dr's. So I can integrate over dr. Well, my radius, the distance that I am from this wire, that can still go from negative infinity to infinity. So that could be a potentially tricky integral. So I don't want to mess with that. Let's look at d theta. Maybe d theta will be a little bit easier. Theta is an angle. Theta doesn't actually go from negative infinity to infinity. The angle that I get, the maximum I can have, occurs at pi over 2. So this theta is going to go from negative pi over 2 to pi over 2. I can integrate over that pretty easily. I can plug that in very easily. So now my goal is really to figure out how to change this dy over r squared cosine theta into some kind of d theta-like equation. And I'm going to do that with a change of variables. So I take my dy, my differential with respect to y, and I'm going to figure out what that is in terms of d thetas. If I go back to my original drawing, I can find that y is equal to x times tangent of theta. I differentiate this, and I find that dy is equal to x times the secant squared of theta d theta. This is some basic calculus that we can do. I can also figure out what is this r squared in terms of thetas. That's going to be equal to x squared divided by cosine squared of theta. Takes some working out to see that, takes some thinking, but you can work this out. You can see this through triangles. If you need help with that, ask me questions. So r squared is going to be equal to x squared times secant squared of theta. And this is really the most challenging part of these kinds of problems, figuring out these changes of variables. They're tricky, and I can't just tell you how to do them. You have to practice them. You have to see them for yourself. If I do it for you, it won't sink in. If you do it for yourselves, then hopefully it will. Okay, so now I've done my change of variables, and I can just plug in all of these things back in to my dEx. So now my dEx changes into a different type of equation. Changes forms. My k and my lambda stay still. My dy, I'm going to do change of variables on the dy. The dy is going to become the x times the secant squared of theta times d theta. I'm going to divide by r squared. Instead of using this r squared, I'm going to plug in terms of my substitution, my change of variables, where my r squared is equal to x squared times secant squared of theta. And then I still need to bring down this cosine of theta times a cosine of theta. Okay, this is getting a little unwieldy, so what we're going to do, we're going to rewrite this on a new slide. So this is just everything rewritten from our previous slide, and what I see is a lot of things are going to cancel out. My secant squared of theta cancels with my secant squared. I have one x up top that's going to cancel with one of the x's down bottom. So now I have dEx is equal to k times lambda over x times cosine of theta d theta. Now I'm going to be integrating over my d theta. So I can take the integral of both sides of this. If I look closely, I'm integrating over d theta. So my variable of integration is theta, which goes from negative pi over 2 to pi over 2. I'm not too concerned about the variables of integration for my dEx, because that's just going to, the integral of a derivative just gives me that variable out. The integral of the derivative is the variable. Then that's going to be equal to k times lambda divided by x. All of those variables are completely independent of my theta. They don't depend on theta at all, so I can yank them out of my integral. And then I integrate from negative pi over 2 to pi over 2 of cosine of theta times d theta. I take the integral of the cosine, and that leaves me with sine. So Ex is equal to k times lambda divided by x times sine of theta from the integral, the variables of integration, negative pi over 2 all the way up to positive pi over 2. I do that integral, I plug in my variables, and I'm going to find that E sub x is equal to k times lambda divided by x times 1, because sine of pi over 2 is 1, minus a negative 1, because sine of negative pi over 2 is negative 1. So 1 minus negative 1 gives me a 2. So E sub x is equal to k times lambda over x times 2. And this turns into my final answer. This example is solved in the book as well. If you can, see if you can figure out if the answer that we have here is the same as the answer given in the book, which is lambda over 2 pi epsilon naught x. And maybe in class, maybe a quiz question will be to prove that these two are equivalent to each other. This is an involved problem. It can be very tricky. It involves knowing and understanding a lot of calculus and doing a lot of math tricks. So make sure you send questions about what parts you do not understand. You'll need to struggle with this. This will take some time. You have to study this. You can't just magically learn it without any effort. But if you have questions, then send them, and I can talk about this problem. I can discuss things that you don't understand more in class. And I suggest, to get further practice with these kinds of problems, read and study example 7. Try to work it out on your own. Try to figure out how the book solution works, how they got what they got, to find that the electric field from a plate is equal to sigma over 2 epsilon naught. Very important problem, very good to understand how to do this, because we will be building off of this in future chapters. So make sure to read example 7, and once again, as usual, ask me questions if you don't understand something. Just a few more things to cover. As long promised, let's talk about electric field lines. How do we draw electric fields? We know how to find the magnitude. The magnitude of an electric field is equal to K times the charge that's creating the field divided by the distance that you are from the field squared. But how do we find the direction? Electric fields are vectors, so we need to know the direction of them. And the direction of an electric field depends entirely on the field sign. If your charge is positive, then the electric field points away from that charge. So in all the examples I've done so far, all the charges have been positive. So if I draw a positive charge, I want to draw the electric field of this charge. Every single field line points in a radial direction, so that's along a radius that's always pointing away from my charge. If my charge is negative, then the electric field points towards. So I haven't done this yet, but we'll draw a negative charge. All the field lines from this go in to this charge. Every single field line goes in to a negative charge. Every electric field starts somewhere on a positive charge and goes away from it and ends up pointing into a negative charge. Another interesting thing about the electric field, the number of lines for an electric field depends on the size of the charge. There's no standard number of lines that come out of a point, but the relative number of lines depends on the charge size. What does that mean? Let's say I have a charge plus Q, and I'm going to draw the electric field of this charge. I'm going to draw one line going up, one line going away left, one line going down, and one line going right. So that means that this charge has 4 lines. 4 electric field lines. Now let's say I have another charge that I want to compare to this one, and it has a charge of negative 2Q. Right away, I want to draw the electric field. I know that the electric field is going to point towards the charge because it's negative. So I'm going to draw my same 4 field lines. They're going to point towards that charge. But the number of lines that I have depends on the charge size. The way I've drawn this right now, 4 lines. I have 1, 2, 3, 4 lines going into this charge that's negative Q. That implies that it should have the same charge as this other guy that has 4 lines. It doesn't. It has double the charge. It has twice as much charge, so it needs twice as many lines. So I need to draw 4 more lines. So I have 8 lines for the negative 2Q charge. So here we should see that the number of lines depends on the charge size. A charge of Q having 4 lines means that any charge 2Q will have twice as many lines, would have 8 lines. Another important point to note about these charges, something I've already mentioned. Let's say I have a positive charge. and it creates an electric field. I have electric field lines that are going to point away, point away, point away, point away. There's all my electric field lines, always pointing away from this charge. Now, the important thing to note is the lines start on a positive charge, but they need somewhere to finish. And all electric field lines start on a positive charge, but finish by going into a negative charge. So they always end on a negative charge. So these guys kind of wrap around so that they can stop, they can close themselves off on a negative charge. This combination of a positive and a negative charge field that's created from these two charges is something called a dipole. Di stands for two, pole is two different poles, positive and negative. You can also think of this as a north and a south pole maybe, if that helps. But this charge is starting on a positive charge, field line starting on a positive charge, pointing away from positive and going into negative. This combination of two charges is something we call a dipole. We also have a way to describe strengths of electric fields. The strength of an electric field depends on how many field lines are passing through a given area. So I have two plates here. I'm going to draw two electric fields. I'm going to draw field number 1. It's got 2 lines. I'm going to draw field number 2. It's got 1, 2, 3, 4. Okay, so I know right away I can look at how many lines are going through each of these surfaces. E1 is a weaker electric field than E2 because E2 has more field lines. So the number of lines describes how strong your field is. More lines equals a stronger field. Less lines equals a weaker field. And the final point to note is that since electric fields are equal to the force divided by the charge, we can think back to Newton's laws. And what Newton found was that force is equal to a mass times an acceleration. So one of the most useful pieces of electric forces, one of the most useful aspects of them, is that an electric force is still going to result in an acceleration. So electric fields can result in an acceleration. So this is really one of the big purposes of electric fields and electric forces. Electric fields can accelerate charged particles. You can make things move by applying electricity to them. And how do we calculate this motion? We can calculate this motion using our tried and true, these things that I told you you would have to know, the 1D kinematic equations. You will never escape these as long as you are doing anything in any kind of physics class. The 1D kinematic equations, remember velocity is equal to initial velocity plus the acceleration times the change in time, where this acceleration is now going to come from an electric field. Or we also have position minus initial position. So the change in position is equal to initial velocity times the change in time plus 1/2 times the acceleration times the change in time squared. Where again, remember, this acceleration comes because of this electric field and the interplay between the electric field, the force, and Newton's second law. And in a nutshell, that is chapter 23.